Okay, ladies and gentlemen, welcome to the November 2024 meeting of the Columbus Astronomical Society. I guess we'll start with our host here.
Thanks. Good evening. I'm Don Stevens. I'm the director here, host for the club. Just a couple brief things. We continue this month and part of next with our public program nights on Fridays, 8 p.m. If you're interested, you can participate in one of those and help out. We will take a pause from those from mid-December through January, resuming in February. It's our winter hiatus. And I try to get a few projects done, get the next year planned out and things like that, our schedule and such. I do plan on doing another series of the telescope workshops that we've done before. Probably do those like in February or March, around February or March. So if you get a telescope or you got a telescope and you want to learn how to use it, I do real basic stuff, teach you about the telescopes and how they work, and get you started down the road on doing that. So there's a fee for it. It's kind of like a formal class that we do. It's usually 2 sessions, 2 2-hour sessions, and I'll make an announcement when I formally get all those scheduled, the dates and things like that. Normally it's around $100 a session. Although sometimes I discount it, particularly for club members. So if you're interested, when you see me post about that, you're welcome to sign up for it. And I guess turn back over to Charles here.
Okay, so we have visitors tonight.
Actually, we just have a couple of visitors tonight. Gretchen, where's Gretchen? There he is, Gretchen. Hi, Gretchen. You're a kind of a tag-along visitor with spouse. And then Scott. Where's Scott? Hi, Scott. You're kind of a tag-along visitor too, aren't you? Okay. A tag-along visitor with. Yeah. Okay. So we're kind of short on visitors tonight, but welcome to our guests.
Yeah. So. Jim, you want to go ahead and?
Yeah, might as well.
Okay, this is Jim Varney.
Okay, for those who don't know me, I'm Jim Varney. I'm the IPP trustee, which is the immediate past president. So it doesn't mean I go to the bathroom a lot, but. I do, but we're having election of officers and that, and as I announced last month, the floor for any more nominations was closed, okay? So we printed in this one who will be nominated, or who is nominated and will be elected. And if you're here, if you would just stand up and let the people know who you are. For the PP trustee, which is a past president trustee, you got Mark Peter. Okay. And 4-year trustee will be Ben Rotten. Am I Roten? Okay. Roten. I meant to catch you before I did this. Ben Roten. Okay. And I guess I got that because of the rotten Ben and.
Is your real name Lyden, by the way? Do you do like the set pistols?
Okay. And the 2-year trustee is Isaac Cruz. And the new secretary that we're going to have will be Bethany Roten. Okay. And that will be done, the election will be done next month at our Christmas dinner. So that's all I've got. Sorry about the name.
Yep. I get it. Doesn't matter. Okay. So Christmas should be fun. We always have a few people bring some musical instruments and sing along and lots of food. You can bring your favorite food too if you want. So that's always fun. We're going to start about 6 o'clock next month, second Saturday as usual. So anyway, Cassius.
Okay, thank you very much.
Isaac runs our,
Hello, everyone. My name is Isaac Cruz, and I am the lead for the Columbus Astronomical Society Imaging, SIG, also known as CAS. And if you're interested to finding out how to take images of, what it's up there in the sky, that's what we try to basically help you with. If you're curious about it, if you've never done it, that's great. If you are, basically a budding astrophotographer and need to actually find out what it takes to take images, take better images and so forth, that is awesome. That's what we're here for. So all types of knowledge are, welcome to it. When do we do this? We do this on the third Saturday of the month. So it'll be next Saturday in this, exactly in this place at 1 p.m. So 1 o'clock, 1 o'clock in the afternoon right here in Perkins. If you have any questions in regards to imaging and, what we do, and, we've been getting a lot of interest on it. I don't know, maybe the comet, of course, we had, the total solar eclipse and so forth. So a lot of people have, kind of like thought about taking, images of what is up there. And, we're here to help you out and get you started on that slippery slope, right? Well, again, thank you very much, and hope to see you next Saturday, 1 p.m. right here. Appreciate it. Thank you.
okay. So, anyway, it's cloudy tonight, but right now is a pretty good time to catch Venus after sunset, and shortly after, Saturn is up pretty high in the sky. So if you haven't been looking at planets, or you're just starting out, this would be a good time to get out your scope and try your luck. It's pretty easy to find them as long as it's not clouded up. And we're going to need a newsletter editor. Yes. So.
Should I get up and explain why?
Yeah.
Yeah, we'll start. Let's see. You guys have seen me before. And I've said many times that I actually wear several hats for the club. One of them is that I'm the current vice president. So regarding that, I'm starting to plan talks and meetings for 2025, and would very much like everybody that is in this room to consider helping out, doing a talk. If you have something that you would like to share with the group up here at one of the meetings, usually we need about 8 or 9 talks per year. That's kind of how it works. I would be very happy to have you. Please get in touch with me after the meeting, or I'll come in and look, give you suggestions and that kind of thing. So that's my first hat. Please help out as a person doing the talks for our meetings. That is my job as vice president. My second job is that I am the director of the John Glenn Astronomy Park, which many of you guys have been to. We are currently selling calendars on Etsy. I was going to sell calendars tonight, however, I had a bunch of things to do during the day and then forgot to put them in my car. So online you can buy them on Etsy, just put in John Glenn Astronomy Park and they come up. It's one of the hits. That would be very appreciated if you would like to help out. It's basically an expanded version of the calendar that is in the prime focus. So that's hat number 2. Hat number 3 is I record the meetings. Hat number 4 is I do a bunch of other little things around the place. Hat number 5, the final hat, is getting, shall we say, a little ratty. It's spent a lot of time. Now it's got a few moth holes and it's getting weather beaten and everything like that. 14 years ago, I took over editing the Prime Focus from Joanne Const, who had done it for about 8 or 9 years herself. And she had done a really good job. And so she passed it on to me. And I've slowly kind of made it into something of my own. It evolved. Many people have helped out. They've sent me pictures. There's a large number of people in here that I can recognize that have helped out by sending me articles and things like that. Thank you very much. But as of this month, the one that I am working on for December, right now, it will be the 168th edition of the newsletter that I have written. And that's a really big number. I mean, if you look at all the different things that I've done in that, I kind of did a cursory summary of all the words that I wrote during that period of time, and I figured that if I took every word that I wrote and just put it in book form, I would have written 8 novels. Yeah, think of all the cookies that I get. Yeah, so I usually write about 2 articles, full articles for the newsletter. I usually write something to describe that picture. I usually write descriptions of the meeting. I do little things to add to the things that people submit to me. I also expand things that people write if I feel like, well, we could expand this a little bit better and that kind of thing. It turned out that something like 600,000 words is what it came out to be. And then if you add to that the fact that I was president in 2000 and 2001, and I've written an article for the newsletter ever since then, it's pushing 1 million words here, which is like 10 or 12 novels worth of stuff. That is a lot of writing. And I think right now in my life that it's kind of time to move on. I'm feeling a little tapped out. I don't feel like I'm as creative as I used to be. And I would like somebody to take up the mantle and do it in their own way. It doesn't have to be the same thing. I hope that somehow what it is now will inspire people to move on, to give them a starting point. But I'm sure that there are some young people here that know InDesign or some other layout and software program and can write reasonably well, or do something creative with video or artwork or something like that can make the newsletter into something new. I mean, I'm an old fuddy-duddy. I've been doing this for a really long time, and I'm kind of set in my ways. So I want fresh blood to do it in a fresh way. Maybe this will help enliven the project and that kind of thing. I've definitely enjoyed it. I've learned a lot from the process. I've actually spent many hours at the library researching things just because I wanted to get things right and get ideas. I've learned how to read the scientific literature in astronomy to find out what's new and interesting going on, and that will inspire me to do something. And every time I sit down to kind of write something, I never know what it's going to end up being like. It's always a surprise to me. And but I've reached a point where my life is so incredibly busy, and I have so many hats that something has to go. And I think doing this for 14 years is about enough. So I'm going to do it for the next 3 months. I'm going to give it 3 months. December, January, February. February will be the last time I do an edition. I'll probably try to make it special in some way. But by then, I hope maybe someone will have decided, hey, I want to give this a shot. And if you are that person, please let me know. So thank you. I appreciate it. Okay.
Okay, so now we have a presentation by our treasurer, Alex McCarthy. And what was the subject again?
Space weather.
Space weather, right. Okay, so the floor is yours.
I was told I've got 3 hours, so I just want to make sure I'm keeping track of time here. I find it funny, the people who laughed at that joke were the same people who've never heard me speak before.
Press is on.
All right, and where are the light switches back there, right?
There's a light there right here. Oh,
Perfect. All right. Nope, that's a little too dark. Or I can do that. This is great. Now I don't have to see everybody's faces as you scowl at me through this, and that's going to work out fine. Folks, my name's Alex McCarthy. Like Charles said, I'm the treasurer of the Columbus Astronomical Society. Been with this group for about 1.5 years now. A little bit about my background. I went to school for atmospheric science, meteorology, got my undergrad, my graduate in that. And when you go to school for meteorology, one of two things happens. You either learn how to forecast and you get a really cushy job in the National Weather Service, or you don't learn how to forecast. I'm one of those people, I can't forecast. I can tell you when something bad's happened, though. So I took that skill set and went into the wild, wonderful world of emergency management. So obviously, I'm here tonight. That means I like astronomy, and I study meteorology. I like weather, and I do emergency management for a living. Turns out that there's actually one thing that ties all three of those together, and that is the wild, wonderful world of geomagnetic storms. Now, this has been an exciting year when it comes to the sun. From the emergency management perspective and astronomy perspective, we spent a lot of time this year preparing for the April 8th solar eclipse, and man, that worked out quite well for us here in Ohio. Not only did we not get crushed by traffic, but the skies were pretty clear. We all got to see the eclipses that occurred. It was great. Then beyond that, about a month later, we get slammed by one of the strongest geomagnetic storms in 3 decades, all right? A lot of us had the opportunity to see the northern lights that night. This is a picture I took at Auroral Observatory in Mansfield, and this is a picture looking due south. I mean, we were hoping to maybe see some auroras peeking up over the northern horizon above the trees. And I mean, they're high above the southern horizon. It was fantastic. I gave this same presentation about, back on September 27th at the Hidden Hollow Star Party at Auroral. And one of the discussions we were having is, what are the odds that we see the northern lights again anytime soon? Less than 2 weeks later, we got hit by the storm on October 10th. Not quite as bad as the one in May, but I'll tell you, looking at, I had a clear view of the northern horizon in Mohican State Park, and it was bright. In some ways, I thought those aurora displays were even more vivid than what we saw in May. Well, geomagnetic storms, sure, they can give us beautiful auroral displays, but from an infrastructure and emergency management perspective, we also want to think about what the potential impacts are on the infrastructure grid. And one of the things that we've noticed in the past is geomagnetic storms can influence the power grid. They can influence communications and even satellites. So anytime we're dealing with the potential for a geomagnetic storm, it's important to think about, what are perhaps some of the downsides. The federal government takes that pretty seriously. Back in the early 2000s, they decided via presidential executive order that we as a country need to think about what a response to a geomagnetic storm might look like. And there we got the Federal Pro-SWIFT Act out of that created what we call the Space Weather Advisory Group. Part of what the SWAG, Space Weather Advisory Group, did was put together a report on what is the state of infrastructure with regards to geomagnetic storms. And they actually just opened up their report, I think it was October 3rd of this year is when they released it. And basically, they just reached out to the different infrastructure sectors out there, and we're trying to get an assessment of what the level of understanding was of geomagnetic storms and what the potential impacts were so that we can try to figure out the future direction of research. One of the cool things that came out of that was that they actually were able to name the storm on May 10th. They called it the Gannon Storm in honor of a former member of the Space Weather Advisory Group who passed away shortly before this. But we're going to refer to this storm as the Gannon Storm. But again, that's the one from the evening of May 10th. So again, the Mother's Day Superstorm, or the Gannon Superstorm, was arguably the most impactful one we've had since the 1980s. It provided a rare opportunity for people all over the country, high, mid, and low latitudes, to be able to see the northern lights, either visually or through camera. In addition, it provided us with a rare opportunity to see what kind of infrastructure impacts we have from these geomagnetic storms. Now, I'm a fast talker. I do apologize for that. That means I also need to pause to breathe from time to time. But this presentation is going to be split into 4 parts. We're going to talk about the structure and composition of the sun. Most of us know that, which is great, but it's at least good to have a brief review. We're going to talk about some of the dynamic processes of the sun. What is solar flares? How do those eventually influence our magnetosphere? We're going to talk about the impact and what that means when the coronal mass ejection hits us, and then we'll end by talking a little bit more in depth about our infrastructure. So, let's talk about the structure of the sun. And when talking about the structure of the sun, I like thinking of it in terms of your inner solar area, or your solar interior, versus your solar exterior. Much like Earth, the sun has a core, though it behaves significantly differently. Constant nuclear fusion going on there, giving off photons. Those photons are going to leave the core, and they're going to spend a stupid amount of time in the radiative zone, kind of bouncing off each other for millions of years before finally getting to the convective zone. This convective zone is behaving somewhat similar to our atmosphere. Here on Earth, warm air rises, cool air sinks. On the sun, warm plasma rises, cool plasma sinks. You get to see stuff sometimes like granules and other features on the sun because of that. One of the cool things about the sun, there's a significant temperature differential in the convective zone. That's a fancy way of saying there's a huge difference between the base of the convective zone and the top of it, and that really influences some of the thermodynamics there of the interior of the sun. Looking more towards the exterior, this is the fun part. This is the part that a lot of amateur astronomers can have an opportunity to visualize and observe. You've got your photosphere. This is kind of what you'll see through a white light filter, where you get features like sunspots, faculae, and granules, which we're not going to cover too much in this. Above that, you're going to get what we call the chromosphere. Your temperature is going to heat up a little bit. That's going to cause your hydrogen to get really excited and emit hydrogen alpha. So through a hydrogen alpha filter, this is why you're going to be able to see things like plagues, filaments, and prominences on the sun. Go further out, on an eclipse day perhaps, you're going to be able to see that solar corona, where you've got streams of solar wind, charged particles, constantly blowing out of the sun and interacting with the solar system bodies. Plasma is not the most common thing on planet Earth, but across the universe, it's one of the most common forms of matter out there. It's hard to really describe it. Think of it as kind of like a gas that has an electrical charge. Normally with gases, you're going to have a proton, neutron, nucleus with electrons surrounding it. When you get into a plasma phase, it starts to be more like an electron soup. You still have your nucleuses in there, your protons, neutrons, but your electrons just kind of, they're not as bonded to those nucleuses as they are with a gas. Ultimately, they've been exposed to so much energy that they've been stripped of their electrons, thus the soup component. But what's nice about plasma is it can conduct electricity, and you're going to find that's going to be the really important component to this. The interior of the sun experiences extremely high temperatures, extremely high pressures, and that's what's going to lead to that ionization of the molecules within the sun. The other thing here about the sun is, like a lot of bodies in the solar system, it does have a magnetic field. Now, I mentioned a few moments ago that plasma conducts electricity, and for those who really love magnets, magnetism and electricity are two sides of the same coin. They're bonded together. So when you have an electrically charged plasma, it's going to influence that magnetic field significantly. Over here on the right side of the screen is a conceptual model for a magnetic field around a bar magnet. And we're going to kind of play a little bit, assuming that the sun and Earth are both bar magnets as a base, and then I'll explain how that kind of morphs a little bit and why. But ultimately, your magnetic field lines will emanate from a north pole over to a south pole and just kind of loop around. This is a pretty good conceptual model for how Earth works, but we'll show in a minute that it's not quite the best show of what happens with the sun. All right? When I talk about magnetic polarity, all we're talking about is what's the orientation of the magnetic field. So what's the issue with the sun? Why doesn't the sun behave like this over here? Turns out the sun experiences something that we call differential rotation. Now, here on the Earth, if you go to the equator, or if you go about 10 paces from the North Pole, you're spinning around that pole about the same rate, all right? Same angular velocity. The sun, however, sees different rates of rotation at the equator versus the poles. So if you're pretty close to the North Pole of the sun, it might take you 35 days to go in a complete circle. Look what happens when you get close to the equator, though. 25 days. You're actually rotating around the sun faster at the equator of the sun versus at the poles, all right? Well, I mentioned earlier, the sun is a huge ball of plasma, all right? Huge ball of electrically charged molecules that are influencing the magnetic field moving at different rates. That's going to cause your magnetic field not to look like that, but instead look like a bowl of spaghetti, all right? So because of this, you're going to have a solar magnetic field that just looks ridiculous. And I'm going to let NASA talk about how ridiculous that is, hopefully. Don, do we have any kind of sound system in here by chance?
Yeah, we can.
My apologies, I was not quite prepared for this, apparently.
Where is your headphone?
Headphone jack right here. Thank you, sir.
Here.
Perfect.
Let's see. I can see.
Not quite.
Hard.
Full disclosure, that is not my computer soundtrack.
Is that the
Nothing against it, it's just not my particular jam. Perfect. Can we turn it up at all?
Sun is a free,
Thanks.
magnetically driven star, but we can't actually see magnetic field lines. They're essentially invisible, and so we have to use some model in order for us to see the structure of the sun. What we're looking at here is one such model, and color coding represents what we call open magnetic field lines, which means that they extend from within the sun all the way out to really, really far out in space. The green and the purple have a north and a south polarity. The white lines are Columbus magnetic field lines, so they come out from the surface of the sun and then they loop around and close near the solar surface. Now you can see how beautifully dynamic the sun is as well. Magnetic field lines interact with each other. They cause big explosions to occur on the sun, and that's one reason it's extremely important to study the magnetic structure of the sun, especially on a global scale. And again, models are the one way we can do this because they allow us to model where the field lines are, how they're going to interact with each other when the sun rotates, and then how that causes solar storms like coronal mass ejection and solar flares. Sometimes the sun is quiet, sometimes magnetic field lines aren't doing a whole lot, but other times you see these bright regions on the sun where you have closed loops, and that's where activity can occur, where the flares can occur. So everything is really magnetically connected.
For those who've never had the pleasure of looking at the NASA Geovisualization Lab, they have a lot of great videos as well as images of not only the sun, but a lot of different solar system. Sometimes we'll have magnetic field lines that just shoot straight out from the sun. They don't come back. Goodbye, sayonara. Other times you have magnetic field lines. They're going to pop out of the sun and go back in. That's how you get sunspots. Sunspots are areas of the sun where those magnetic field lines have punctured through. All right? The magnetic field lines are going to come out one side and go back into the other side. And as they come out and go back in, they're going to channel a lot of those high energy particles from the surface of the sun into loops. Because of that, what's going to happen is the areas on the surface of the sun around these magnetic field lines are going to become a lot cooler because all those hot particles are being pulled away. And because it's cooler, they're going to appear darker in color than the surrounding sun around it. Now, these sunspots are not pitch black. Turns out that if you got rid of all the sun except this area right here around this where the spot is, it's going to be about as bright as a full moon, magnitude -12, -13. So sunspots are still incredibly bright. But when you're looking at the luminosity of the sun around it, completely different. So, fun fact there. Sunspots can be classified in a lot of different ways, and unfortunately, I'm not going to go through each of these, but just be aware there's different classifications of sunspots, and if you ever read any forecasts out there by the Space Weather Prediction Center of current sunspot activity, this is what they're referring to, and you can find some easy guides online that break those down. The number of sunspots on the sun are going to fluctuate with time. We call this the solar cycle. Right now, we're pretty much at the peak of our current, here we go. Sit down. We're getting about to the peak of our solar cycle right now. I think NASA put out a news release last month saying they think we've reached the peak of it. But basically, right now, if you look at the sun any given day, there's going to be multiple sunspots. In about 5 or so years from now, we're going to get to these lulls where you might have only a couple, maybe a dozen sunspots in a given year, so the sun's not nearly as active. Our current cycle is reasonably active one. It's not quite as active as 100 years ago per se, but we're seeing a lot more sunspots and a lot more geomagnetic activity during this solar cycle than we've expected. If you go back about a decade between like 2005 and 2012, that was a pretty weak solar cycle. There wasn't really a whole lot that happened. Now, what's relevant to us right now is we've already had 2 major geomagnetic storms. I was chatting with Jason earlier before the meeting. In addition to those 2 major geomagnetic storms, there have been 2 days this week where people have actually been able to photograph northern lights here in Ohio. I was camping the week of October 10th when we had the last major geomagnetic storm. In addition to that storm on Thursday, I was able to photograph auroras on Monday and Tuesday, and I also saw the auroras on Tuesday evening that week, just we had a real brief spike in a storm. These are really common right now during the solar cycle. They're not necessarily going to be these clearly visible auroral displays up in the sky, but they're actually pretty common compared to other points in time. The strongest solar flares tend to happen right after solar maximum. So I would expect that the strongest solar flares in our cycle statistically should be probably between January and July of 2025. So what that means is I still think we're going to have a couple more major auroral displays here before we get to the end of this solar cycle. So do look forward to that. Now, the one challenge is I've mentioned that there's been a whole lot of solar cycles that we've been monitoring since the 1700s. The intensity of a given solar cycle does not indicate the likelihood of seeing northern lights, nor does it indicate the intensity of solar flares. You can have really intense solar flares occur in a very weak solar cycle and vice versa. But the point is that if we're going to see some more intense solar flares, the next half year to the next 6 months to a year should be when we see some of the bulk of those. So do look forward to that. Well, let's talk about what a solar flare is. To get into solar flares, we've got to talk a little bit more about sunspots. Sorry about that. But with sunspots, sometimes they're small and boring. Other times they get a little more interesting, for better or for worse. And if they start to get more magnetically complex, we start to call them active regions. The Space Weather Prediction Center will start labeling them as active regions. Now, in active regions, not only do you basically have magnetic field lines leaving the sun and going back in, but you've got really complex physics going on in those sunspots. And because of that, the magnetic fields within these sunspot regions tend to be pretty complex versus like individual sunspots. And when they get very complex like that, they'll be called an active region. Point is, if we're looking for anything that's going to cause a solar flare that will make things interesting here on Earth, we want to look for the ones that are categorized as active regions. Every day, the Space Weather Prediction Center puts out a statement that talks about the active regions that are out there. So they're going to give the active region a number. They're going to talk about like where on the sun they are, what the size is, and what the magnetic classifications of those sunspots are, which I'm a nerd. I think it's pretty cool. I also like weather enough that I enjoy reading the very basically structured forecast that are put out. So in early May, one of those particular active regions started to become kind of noteworthy, and it was called Active Region 13664. Now, normally what they'll do is they'll cut out that 1, so 3664, you just pretend that 1's in front of it. They do it for simplicity, I guess. So Active Region 3664 became very magnetically complex and started throwing off a lot of material through various solar flares. Now, I want to show you guys a little bit about the evolution. This is about a week of imagery here. May 3rd, you have a beta class, which is kind of a more basic classification of sunspots. You can see it's pretty magnetically complex. We've got a lot of different pairings of sunspots in there. But over the next couple of days, it just kind of grows and gets weirder and weirder. Now, we talk about these sunspots can be very large. I see every once in a while NASA will put out a graphic that shows a sunspot with planet Earth next to it. Planet Earth would probably be about the size of that maybe. But on the grand scheme of how big these are compared to the sun's surface, even at its widest part, like 0.05% of the sun was covered. So even though these things are massive, the sun is so massive that it's barely even taking up any space on the sun. Just a little fun fact. So when we talk about solar flares, the first thing I want to put to bed is Earth does not get hit by solar flares. we'll get hit by something called a coronal mass ejection that's put out by a solar flare, but in simple terms, a solar flare is basically just an explosion of light that will push stuff out. Now, flares are eruptions of electromagnetic energy from the sun that happens when energy builds up in unstable magnetic fields. So if too much, they're still not entirely sure how this happens, but the leading theory is if too much current, electrical current flows over a coronal loop, one of these magnetic field kind of things, it's going to begin to bend, kink, and break apart. And when it stretches, fails, and breaks, it's going to release a lot of energy at once, and that's that solar flare. Let's visualize this. This is just kind of showing that underneath the sun, the physics will start to push these magnetic fields up towards the surface of the sun. As they penetrate through, you get the sunspots. All this material gets thrown up, and it cools down. Over time, these get complex, and sometimes they kink like that and break. It's going to shoot off particles towards Earth. We would call that the coronal mass ejection. But the solar flare itself is basically, again, just light. Now, we can observe solar flares in terms of visible light. That's how they did it way back in antiquity. But really, these are best observed with X-ray, by looking at X-ray or ultraviolet emissions. And we use the Solar Dynamics Observatory suite in order to do so. I'm going to go ahead and play this video, which okay, yeah, that actually is going. So just kind of watch what happens. I believe it's going to be this sunspot right here, or that active region right there. See how it just gets really kind of bright like that? That's a solar flare. It's not the most exciting. If you're paying really close attention, it's hard to see, but you'll actually see some material get ejected off. But really, that material is a coronal mass ejection. The solar flare is just the light that occurs when that magnetic field line kinks and breaks. Now, solar flares are kind of categorized on a 5-point scale here. So we would call it like an A, B, C, M, or X class flare. In terms of looking for northern lights displays, we're usually looking for M or X class events. And this is basically measuring watts per meter squared worth of electromagnetic flux being detected by some of those satellites. Point is, in the period of about 2 weeks, there were 12 X-class solar flares. For those who like tornado or hurricane scales better, this is like a Category 5 or an EF5 tornado equivalent. So 12 X-class flares from an active region is pretty notable. What's also notable is that the baseline was basically, there's a continuous C-class flare for like 2 weeks, and everything that was being burped was just heightened flaring above that. So, you know, pretty intense, pretty significant in terms of solar event activity there. Now, why should we care about solar flares, even if it's not directly causing the northern lights while it's occurring? Turns out they'll degrade communications, all right? Electromagnetic energy released by solar flares is going to ionize atoms and molecules in our upper atmosphere. And what that can do is cause a little bit of a communications blackout for various types of radio frequencies out there. These radio blackouts can last anywhere from several minutes to several hours, and there's no real way to provide much lead time to these blackouts. The best that can happen is the Space Weather Prediction Center will say, like, hey, there's an X probability of a C, M, or X class flare today, but there's nothing that can say, hey, in 1 hour from now, you're going to lose these bands. Anybody in here an amateur radio operator? I know Jason is, Isaac is. Man, would have thought a lot more folks. Oh, well. So, let's talk about why this is important. When we talk about ionization, normally you've got all these molecules with electrons around them. When you ionize that, again, the electrons are kind of stripped. The atoms there will live in an electron soup. And it turns out that it increases the density. So obviously there's a little more density in this graphic than that graphic, thanks to the constant movement of electrons all over the place. Now, your ionosphere refers to a couple regions in the upper Earth's atmosphere where solar energy during the daytime is going to ionize those atoms and molecules and create different layers. Now, note that the ionosphere is not a separate layer of the atmosphere, but basically regions embedded within the atmosphere where this ionization occurs. And that's going to be from the radiation of the sun, of course, especially as it changes from day to night. And this is what influences our radioactivity, all right? During the nighttime, you've got two layers, essentially, E and F. Sun's facing away. There's not as much solar radiation coming. But during the day, That's where it really starts to get complex. More on this in a little while, but when we get these radio storms, there's 5 levels. This may change in the near future, but basically, anytime we're talking weather or space weather, hurricanes, tornadoes, radio storms, geomagnetic storms, it's a 5-point scale where 5 is the worst. All right, so what's up with communications? If I'm over in California and Jason wants to talk to me over ham radio, what he's going to do is try to bounce a signal from him, hit the ionosphere back, and find me. All fine and good. I know this is simplifying things, but it's what it is. Let's say, though, that we have a radio storm going on. That solar flare is occurring. It's sending additional electromagnetic radiation our way. It's going to ionize that D layer. When Jason tries to get that signal up, it hits the ionization layer, and that takes away the energy of that radio signal. It can't pass through, it can't bounce off, and I'm not going to know what message Jason's trying to tell me. The good news is for most communications that we use on planet Earth, this isn't that big of a deal, but it will impact some ultra-high frequencies. But basically the way this just works is that normally the highest frequency, for instance here, that would be degraded by the sun on a normal day would be like 15. So you'd have to really go to maybe 20 or 25 megahertz in order to communicate. If we're dealing with an ongoing radio storm, like let's say I'm over in India, basically I'm not able to use any of these frequencies. It's all being degraded. That's the first way that this can actually influence us here on Earth. Here's the other thing. Solar flares may initiate coronal mass ejections. So, obviously, right up here, we have an active region. We can see that there's a lot of magnetic activity going on. We've got a lot of particles suspended above the sun, right? Watch this. All that just gets shot up into space. Now, the solar flare is happening at the same time, mind you, but this better illustrates you've got a lot of material that's shot up into space. Some of that material does get drawn back in, which is normal, but again, the point of this slide, there's a difference. Solar flare versus coronal mass ejection. And it's that coronal mass ejection that's coming our way. So, say for the sake of time that I'm looking at my phone and I see that we've just had an X3.5 solar flare. That's significant if that had happened. So now the next question is, which way is that going? If somebody nearby shoots off a gun, I want to know is it pointed at me or pointed somewhere else, because that's going to lead to a whole different set of calculus in my mind. So this is LASCO imagery, and what we can do is see, is it Earth-directed or is it going somewhere else? If it's going somewhere else, like in this graphic, you're going to see all that solar material just go in some other direction. But if it's coming towards us, as you watch this image, it'll start to spread out and kind of look like a bullseye getting larger and larger. That's a sign it's incoming. I'm going to show you guys a video here, and this video is going to show a non-Earth directed coronal mass ejection followed by one that is directed towards Earth. So keep an eye up here first. There it goes. That one's a little different. See how that spread it out? I'll play this video one more time. The other thing is see how it gets really staticky. That static is radioactive particles basically hitting that satellite. We'll give that one more try. Here goes the first. Here comes the second. So, apparently a third non-Earth directed one in there. That's cool. So, I mentioned earlier, there were 12 X-class solar flares in a 2-week period. Turns out you don't just need X-class solar flares. You can have M-class, or moderate, you might say, class solar flares still lead to coronal mass ejections. I think earlier this week, the one that we got hit by, like yesterday, I think was from a C-class flare. Generally speaking, the stronger the solar flare, the stronger the coronal mass ejection, but it really, there's a lot that goes into it. So there were 19 coronal mass ejections during the first 2 weeks of May. Of those 19, 10 were directed towards Earth. Here's an example of 4 of those. And you see there's a mixture of some C-class solar flares and an X-class solar flare. And the whole point is the ones that are Earth-directed, you always kind of get a little bit of a halo effect. I don't like the orange as much as the blue because it's harder to see, but it's what I was able to access. One of the things that's challenging for some researchers right now is they're trying to figure out which of those 10 Earth-directed coronal mass ejections actually caused our northern lights display on May 10th. And there's a lot of interesting things that happen. Solar flares in space can actually interact. They can also act like bulldozers and clear out the little dense stuff that we do have in the solar system as they move on. And what's likely is you probably had a couple of these coronal mass ejections interact and actually bump into each other on their way towards Earth from the sun. So it's likely that an X-class and a strong M-class flare that occurred on May 8th probably merged together at some point. The first of those coronal mass ejections would have left the sun, and as it runs into particles and stuff in the inner solar system, it's going to slow down a little bit and kind of clear those out, meaning that the second one can go a little bit faster and eventually bump into it. They're just not sure. It also probably merged, those two probably then merged with a third X-class solar flare that occurred the day before, and basically just led to this whole kind of mush of stuff hitting Earth. Again, some research going on there. So, jumping back into this. The solar flares occurred. We know from the satellites that it's heading our way. What's the next thing we can do? Well, we can use the WSA Enlil model to figure out kind of what the timing is going to be of this, as well as how dense that material is going to be, how fast is it going to be, and that's going to influence what kind of hit we might take. Now, I like weather models, so we're going to talk a little bit about this. Basically, you've got two models that work together to create this output. One's going to look at the velocity and the propagation, the direction of the solar flare, the direction of the coronal mass ejection, and then one is going to look at kind of the boundary conditions and magnetism. But basically, in order to figure out what the propagation impacts are going to be, two models feed into it, which is kind of cool because it's easy for us to develop weather and atmospheric models. This is a lot harder because all of our source data for any space weather related forecasting model comes from two-dimensional images, two-dimensional pictures. Whereas if we're trying to predict the weather tomorrow, we put up weather balloons. We've got airplanes at all points with temperature and humidity sensors. We've got three-dimensional data inputs for three-dimensional atmospheric models. We just can't do that yet with space weather, unfortunately. So here's a model run for what was being expected for the afternoon of May 10th. Actually, before I play this, just so we're clear, this graphic here, we're looking horizontally towards Earth. This graphic here, we're looking straight down at Earth. So it's trying to give us a three-dimensional representation. And basically, what it's saying is around 11 Zulu time, we're talking kind of in the morning hours, we're going to take that first hit, and then we're going to take a few subsequent hits. Let's watch that again. Hit, and then another hit. And honestly, I've been watching these kind of models for a while. That was one of the stronger model outputs I've seen in terms for, hey, you guys are probably getting a show out of this. So let's talk a little bit about impact, all right? It's all fine and good that we now can use a model to figure out when approximately this is going to hit us, but there's one last data point we need to know that we can't measure until it's really crazy close, and that is the magnetic polarity of that solar flare. Ah, yes, not solar flare, coronal mass ejection, wow. So yes, that coronal mass ejection, that blob of charged plasma gas heading our way, has a magnetic field around it, all right? If that magnetic field is oriented north, like planet Earth, it's going to hit us and be rather boring. If it's oriented south, it's going to be a little bit more interesting. And we will not know the magnetic polarity of the coronal mass ejection until it's about 1 million miles away at the Lagrange 1 point. That means we've got about an hour heads up between when the solar flare hits this and we can get an actual measurement of what's going on there until it hits Earth. That's going to be a little bit important later on when we talk about how some of the electric and power companies prepare to mitigate their infrastructure against a solar flare hit, because that means they essentially have 1 hour to call the play and take care of business. But yeah, this ACE satellite is what gives us this. If you've ever seen this kind of graphic on social media or on the Space Weather Prediction website, this is telling us what the solar environment is at a given point. Now, this has been broken down to be specific around that May 10th solar storm. A couple things here. This is going to tell us how intense the magnetic field is. The white line here is going to tell you the intensity of the total magnetic field. What we really want is what we call the BZ value, the vertical magnetic field orientation. So in this case, you'll see that it goes down around -50. If you want to see a good northern lights show here in Ohio, I want to see that red line about -30 at least. Anything positive doesn't really count. Phi, I don't pay much attention to this. This is just kind of like the angular direction of the polarity of the field. You want to have high density, high speed. I don't care about temperature, but density, speed, and strength of the magnetic field are the three most important things. Now, you'll see with the density, it was already pretty high because we're almost in a solar maximum period at this time. So there's constantly going to be particles from the sun heading towards Earth. What you see here in kind of the morning hours of May 10th is the density ramps down and then starts to ramp up over time. Ahead of that coronal mass ejection, things are going to be piling up, and that's why suddenly you'll see density start to rise over a period of time until you get your actual hit. Notice what happens here is my speed goes up significantly from like maybe 400 kilometers an hour all the way up to 700, just like that. Temperatures also go up. So right here, just without looking at magnetism, I have hot gas suddenly just hit that satellite like a bat. Up here, at the same time, my magnetic polarity just goes down. It's a very intense magnetic field. I mean, we're talking negative 50 newtons, or nanoteslas. That's pretty intense. So anybody here who ever decides they want to go auroral hunting, this is probably the most important tool because this gives you your hour forecast, all right? Whatever's happening right here, right now, will take about an hour before that's actually happening here on Earth. So, Earth's magnetic field. Unlike the sun, which is, I like to call it the bowl of spaghetti model, Earth is pretty much like your conceptual bar magnet model. Now, thanks to the solar wind constantly blowing this way, part of the magnetic field is going to be shoved this way, but in general, coming out of the north, looping around, coming into the South Pole. Now, what happens when the CME hits Earth? Sorry for walking around, Brad. No, I'm giving you your Earth. The magnetic sphere on the day side is going to be compressed, all right? So, unfortunately, when it first hits Earth, whoever's on the day side is going to be seeing sunlight, not northern lights, but these magnetic field lines, the gradient compresses, that's going to energize all the charged particles that are lofted in the upper atmosphere. And those highly charged particles, as they get charged, they're going to head towards the poles. And that's where you're going to get your initial auroral display. Your coronal mass ejection is going to pass. And as it passes, it compresses these lines down over here. As they compress, electrically charged particles get excited, energized, and they shoot back as a secondary show. All right? So, two things out of that. First off, when we see the northern lights, most of those charged particles that hit our upper atmosphere are those that were already in the Earth system. We don't really take a lot of energized particles from that CME. It just energizes the ones that are already in our Earth system. And secondly, we always take kind of two consecutive hits at the same time. Now, it's not like multiple hours between this and that, because that coronal mass ejection is going to move through pretty quick, but I mean, we've got a three-dimensional kind of storm going on. Let's visualize this a little bit differently. This is going to pretty much to show you how everything gets compressed as the CME hits us. Here it comes. Everything in there is going to compress as well. Patterns and colors in the northern lights. Two things here. The first and the easy one is let's talk about colors. Usually they're going to be red, green. Sometimes you can see some purples and blues. I've never seen that before. What's going on here, though, is that different types of molecules in the atmosphere are going to get ionized, and when they're ionized, they'll emit different colors of light. Secondly, the auroral shows actually have just a little bit of a diurnal pattern to them. Diurnal, what does that mean? Throughout the evening, things are going to change. Right around sunset, you're going to have kind of boring aurora, You're going to have very non-moving aurora. They're going to be generally kind of like arcs, not moving very fast. If you're doing photography, you can kind of bump up your shutter speed a little bit. Then they start to get more active as time goes on. This is where you start to see some of the very vibrant colors, some of the crazy movements of the aurora. And then by early morning, they start to get a little bit more patchy. Now, this is all dependent about the timing of the CME hit and other things, but this is generally what you can expect. Now, looking at May 10th, I said earlier, it was rather impressive in the last couple decades with just how many people could view them. Now, this was from one of the GOES satellites that typically does weather, but the aurora were kind of centered over the northern United States. I mean, even in Ohio, northeast Ohio and central Ohio, they were straight up. Kind of unusual. We don't see that too frequently. I saw another presentation that I was not able to pull the slide from, but it was an AccuWeather graphic where what they did was for each state, they put up a picture of somebody's northern light shot from that state. So instead of seeing the lights here around Florida, it was showing the outline of Florida with the actual shot. Point is, somebody in every state in the United States, Hawaii included, were able to see the northern lights. Here's an image of global auroral observations, complements of, I'm not going to try to pronounce that name, but this is from an analysis of the event. And if it was red, that's a visual observation. Blue was a photographic observation.
How?
Hayakawa? Perfect. They, if you guys are interested in space weather, this is in my last slide here, the bibliography. That was a fascinating read just about the whole extent of this. And it's not very scientifically difficult. Point is, though, again, a lot of different people were able to see it. So let's talk a little bit about infrastructure impacts to wrap this up. Human and infrastructure impacts from space weather can happen in a variety of different ways. Now, I've basically been covering kind of your solar flares and coronal mass ejections and what those do. Also note that there's a feature on the sun called a coronal hole. These become a little bit more prevalent as we get to solar minimum. We have had some coronal holes later. Basically, all the coronal hole does is instead of magnetic field lines looping back into the sun, it's a compact grouping of magnetic field lines that just shoot out into space. And you'll see very fast and dense solar wind with that. And sometimes it can cause the northern lights to start to drift south again. But this graphic here just kind of talks about some of the different types of impacts we can have and what's important. You can have issues with satellites and issues with humans who are in space, especially if we're dealing with radiation storms. You can have hazards with aviation for those flying around the poles, issues with telecommunications, broadcasts, and radio communications, GPS, as well as power grid issues. So breaking these down, the first and the most obvious one for most people is the power grid. It can be vulnerable to solar activity. And there's no shortage of past events that show this. The first time that geomagnetic storms were really kind of noted here in the United States was in the 1860s when we had an event called the Carrington event. Anybody ever hear of the Carrington event before? Basically, 1860s, spoiler alert, we did not have a whole electrical grid at the time. We had just started to put up telegraph lines across the country. Now, some astronomers had known that there were a lot of solar sunspots on the sun, and then suddenly you had northern lights in the Caribbean, okay? Telegraph wires in some spots were spontaneously combusting. That just shows really interesting, really powerful event. If we had a power grid at the time, that would have been interesting. Some other ones of importance, Quebec 1989, that was probably the last really strong solar storm. Let me put that a different way, because 2003 was really strong. Quebec would have been the most powerful storm, I'm not going to say it that way. Point is, 89 and 2003 were the last two major solar storms before the Gannon storm, and both of them saw regional power outages and power grid failures. Basically, what happens is that you can have induced electrical currents at the ground because of the Earth's magnetic sphere taking that hit from the sun. Earlier I mentioned that you've got, anytime you've got an electrically active plasma, it will induce a magnetic field. Vice versa, if you've got a really active magnetic field, it can induce electrical currents, and that happens in the ground. As electrical currents are induced, it gets pulled into the power system, and your extremely high voltage transformers will sometimes not be able to accommodate that, and they'll basically overheat and get damaged. One of the problems is we've got over 2,000 of these EHV transformers, extremely high voltage. Oftentimes they're custom built for the particular facility, and it is hard to replace those. So from an infrastructure standpoint here, if we're having an induced electrical current at the surface and a lot more electrical current getting pushed into our power grid, we want to make sure that we can isolate those transformers and not cause them to overheat, get fried, because it's going to be difficult to replace them. So solar plasma from a coronal mass ejection is going to interact with the magnetic field. It's going to induce electrical current, and different parts of the country are going to see different levels of electrical current. I believe this is a graphic from just a day-to-day kind of period of time where there's just not a whole lot going on, but that can always change. There's some debate right now over the actual extent of power grid damage from the global electric current. In the early 2000s, there were some studies conducted that said, yeah, in the event we got hit by the Carrington event, probably about a third of those transformers would get wiped out. and it would take months or years to replace them all. Homeland Security really started to look into this in the early 2010s. I mentioned earlier, that's when the executive order came out that said the federal government shall look into this and shall mitigate against it. Well, there was some issues with some of the initial data that had been used in prior studies that the Department of Homeland Security kind of thought maybe it's not quite as bad as was initially said. A NERC report was a lot less aggressive as well on the number of transformers. It said a lot of them might be taken out, but the impacts would not necessarily be as long-lasting. More recently, some of the studies have said that in a wide-scale significant impact, we might have about 50% of U.S. let me put that differently. In the event of a major solar storm with major outages, they estimate about 50% of customers will be back within the first 12 to 24 hours. So there isn't as much concern, it seems, among a lot of these professionals in terms of how much of the power grid could go down in a major geomagnetic storm. It's still something that is considered and discussed a lot behind the scenes, but I know I talked to some people who are like, yeah, if the Carrington event happened, all humanity would basically go extinct. Probably not. The one challenge we do have, though, is that there's model limitations, all right? A lot of research is being done right now to try to create models on how a solar storm, how much geomagnetically induced current would, let me try this a different way. There's a lot of research right now on how to develop models to show how this globally induced current would actually enter into the power grid. We don't really know how all this would play out. And it's difficult to figure what the impacts on the electrical grid would actually be. And the other problem is we don't have a lot of data points of significant geomagnetic storms hitting us with our modern grid. Now, do note our power grid is always changing. It's a lot more complex right now than it was in the 80s. And because of that, there's still a lot of uncertainty. So I don't lose a whole lot of sleep over geomagnetic storms destroying humanity as we know it, but it is something we need to keep in the back of our heads. Another thing that I sometimes will hear folks talk about is how, of course, geomagnetic storms would take out power. They're just like nuclear weapons. Not quite. If we start to look at geomagnetically induced current impacts versus EMP from nuclear blasts, your geomagnetically induced current really is looking for large-scale infrastructure to hit up. So if we got hit by the Carrington event right now, you'd be able to call me to tell me it happened. Your cell phones are not just going to explode in your pockets. If we have a nuclear blast, though, like an EMP blast maybe 100 kilometers above us, there's 3 phases to an EMP, 2 of which can significantly impact even your small devices like your cell phones. But really, with a geomagnetic storm, we're looking for large-scale infrastructure, power grids with millions of miles of wires, rail lines with millions of miles of metal rail, pipelines with thousands of miles of metal pipe. Those are where this globally induced current can get pulled in. You can have issues with the transportation of natural gas or even fluids through your pipeline infrastructure. Your rail lines can have all sorts of disruptions when they get energized during these storms. Those are some areas people don't always think about, but it's those large-scale infrastructure that would be most impacted. From the Gannon storm, here's an example of what the globally induced current was like across the country. A couple things to know. Not all rock is created equal. Yeah, it's rock that really influences your geomagnetically induced current, but you've got some areas that take extreme impacts. Other areas are a little bit more resilient, all right? In particular, Ohio's not the worst place in the world to ride out a Carrington-level event storm. I would steer clear of the northeast seaboard. Another thing I've heard in the past is that areas like western North Carolina, South Carolina also have infrastructure that is a little bit less resistant to these kind of events, and that's another area that could be hit kind of hard. It's all about the geology of the rock around it. Well, electrical infrastructure is not the only one that took a little bit of a beating with the storm. And actually, if you read into the literature, a lot of the power companies were able to easily note that we were dealing with the major solar storm, but there weren't any real significant power issues across the globe that I've heard of so far. Department of Homeland Security and their infrastructure branch put out a request for information to local companies back, I think, in like June or July, and I don't think there were really any significant things that were reported at that. So unlike 1989 or 2003, there weren't any like regional power outages that occurred around this. It's just if you were in a command center for one of these power companies, you could tell that there was some globally induced current being pulled in. And part of that, I think, has to do with the fact that power companies really do take this stuff seriously. There are a lot of discussions behind the scenes about how to deal with these events as they come in. But again, the key thing with geomagnetic storms is going to be that orientation of the magnetic field. If we have a major solar flare occur that we know has a big coronal mass ejection, we need to know what is the magnetic orientation of that coronal mass ejection, and we're only going to have about an hour heads up about what that really is. And that in some cases is going to be the difference between no impact and significant impacts. So usually what will happen is that when there's a major solar flare, the Space Weather Prediction Center and FEMA will be talking directly with these power companies, and kind of the last go, no-go decision is once it hits that ACE satellite, that is where the Space Weather Prediction Center tends to let the power companies know what's going on. Communication and GPS infrastructure impacts. Basically, like I said, with radio communications, it gets degraded when there's ionization going on. Northern lights, that's ionization. They'll degrade communications in some cases or kind of change how the atmosphere behaves. And that can influence your GPS a little bit. So a lot of agricultural work was being done in May. It's plowing and planting season for some folks. And there were some issues with a lot of farm equipment that relied on GPS. This, I believe, was from the Dakota area. Yeah, South Dakota farmers. There's just a lot of erratic activity with tractors. So that is kind of one of those interesting things. My dad still uses a GPS, little device from 2003 that hasn't been updated. So I'm used to a GPS trying to drive me through a lake. Other people might not be used to that experience. So just, all that can be kind of interesting. It's okay. Dad doesn't watch these videos, so he'll never know. Aviation impacts from solar storms. Basically, when these particles are heading towards the poles, there's an increased amount of radiation. So it might be the equivalent of getting a few chest x-rays. It's not going to send somebody to the ER with acute radiation syndrome, but over time, these could have an increasing impact on pilots and airline staff, flight attendants and all that. I gave a presentation similar to this in an emergency management conference a few years back, and one of my colleagues had previously been a weather forecaster for the Air Force over in Fairbanks, Alaska. He pulled me aside afterwards and said, the Air Force takes this stuff seriously because they've got pilots constantly doing sorties over the North Pole. Over time, this stuff does add up. I've always had 2 feet on the ground, so I haven't had to worry about this as much. But there were some great discussions I've seen since the Gannon storm about what level of concern should the airline industry have over this? Should this be considered when we're thinking about hazard classifications for workers and all that? And I think there's some great discussions to be had. How about I grab this? Sorry, I'm a walker. And the other thing, of course, is that this was actually an opportunity where they had some actual measurements of what the radiation impacts were on airplanes. And it wasn't anything too significant, but this is some data from a private sector source, I believe, and it was just kind of cool that somebody actually measured it for a change. This was the one I thought was the most interesting out of this. 1989 and 2003, we had some satellites in space, but that was before the era of Elon Musk and the constellation of his satellites up there. We actually see some pretty interesting graphs right now about how the coronal mass ejection actually influenced satellite orbital altitudes. When those particles hit Earth and you get all that ionization and that increased density up in even where some of these satellites are moving, that's going to slow things down a little bit. And you can actually see, like, any given day, there's going to be some orbital decay among satellites. I mean, we're looking at portions of a mile a day. The night of that solar storm, we go from, 486 on average kilometers above Earth down to 485. So, I mean, that's a decrease of about a kilometer in a very short period of time. And these different industries that have satellites up above need to be focused on this because that can disrupt satellite constellations, that can put satellites in danger of hitting each other and create all sorts of other hazards. But this is the first real event where you've got just a really nice, statistically large data set to work with. I did not include anything in this presentation from the October 10th event. However, it was another example similar to this where people were able to show data about how these orbital decays all kind of came about. So moving forward, this is something that industries that put large amounts of satellites into space need to be aware of because it's going to create all sorts of impacts for them. Let me see. Here's just some example of satellite drag. And the number of maneuvering satellites at any given time is not zero, but maybe a few hundred. You went real quick from a few hundred satellites you're maneuvering to get back up to altitude to a few thousand, like almost 5,000 at once. This is the Halloween storm, late October 2003. What is that, 30 satellites trying to get back to their altitude after a solar storm. So needless to say, 30 is a little bit different from 4,000. Drag implications among satellite classifications. This basically just kind of shows the operational payloads, debris, and rocket bodies, what the typical degradation was of these. And you see that some orbital payloads ended up after the storm a little bit higher in altitude because of overcorrection probably, but a lot of things, especially space debris, I mean, it went down. You've got some things almost came back into Earth's atmosphere. So, I mean, you've got, no, excuse me, that was the wrong way of reading that. You've got some that went down nearly 10 kilometers throughout all this. So, again, satellite drag, satellite implications are going to be really big as we move forward dealing with geomagnetic storms. So, let's summarize all this. First off, again, the Gannon storm was one of the most intense solar storms in 2 or 3 decades. Still some argument about how it compares to 2003 and 86, but probably a little bit weaker than 86, but not by much. The aurora were visible over much of the world, either visually or through the use of a camera, and this is a rare opportunity to gather information about how space weather will impact infrastructure and humanity on a different day. Lastly, while infrastructure was generally resilient with the storm, still some research that needs done. I think that obviously the satellite stuff is interesting to me because that was not something I expected, but with the power grid, it is something that we all need power. So we want to make sure it's resilient enough for any kind of solar storm because it is an inevitable hazard. We will deal with another Carrington-level storm at some point or another. Last one, there's references for further reading. I'll give my slides over to Brad, but for anybody really interested in space weather, the things I included on this bibliography are papers that were not terribly difficult to read, and some of the ones that were rehashing the May 10th storm had a wealth of information in general about how space weather works and all that, and I highly recommend it. So with that, before I ask for questions, I am going to preface this. When it comes to space weather, I am an enthusiast, which is different than an expert. So I don't claim 100% accuracy on here, but I'm trying. I think I've got things pretty well covered. So with that, I'll take any questions you folks have. Yes?
SpaceX did lose 12 satellites in the May.
Man, it makes me safe that way as an astrophotographer. But with the amount of SpaceX satellites out there, 12 is just a really tiny number there. What other questions or comments we got? Mark?
So you were talking about when you're most likely to see the intense auroral displays as far as time of night.
Mm-hmm.
And is that, does that have to do with the position of magnetic north or is it, I've seen the aurora oval, how it kind of rotates around, but I don't understand, why is it early in the evening that you're more likely to see
Well, yeah, I can answer that. Magnetic north is not located at the North Pole. It's actually displaced, it's in the Arctic Ocean just north of some of the small islands up in Canada. And that's why the oval's sort of lopsided, and that's why it's able to reach down as far south in North America as it does. And the other effect you get is because at nighttime when the sun's over here and that mass is incoming, it pushes our magnetic field back. As Alex talked about, the current flows along those magnetic field lines. And this, if I get up here, go ahead. Yeah, this is this part will be stuff coming in from the front end. This is what happens back in the magnetic tail. All right, when you get those magnetic line recombinations, that it flows back towards us. And that's why the timing's kind of critical because it's traveling, at 700 kilometers a second. So when it hits here, well, a good example is actually that day before, Europe and part of Asia got a better display even than we did that night. Because of the timing, that's when the material first hit our magnetic field. And then at 700 kilometers a second, you know, we got the good part of the back end after most of the material already passed by the Earth and was affecting our magnetic tail.
Yeah, sure. So when we actually see the predictions, like, basically that, the oval, those are based on the information that we get from that satellite, basically.
I actually don't know what goes into the Auroral predictions. I'll be honest, I don't typically use it that much.
I know what goes into it. There are 12, and a 13th one that went offline, but 12 different magnetic stations spread around the globe. There's 4 in North America, 6, I think, in Europe, one's in Russia, and then there's there's one in Australia and one in like Tierra del Fuego or something like that. And they combine the current signal, the current magnetic signal on the Earth from all of those, and they create a model of the intensity of the aurora at different locations for that particular time. So it's actually, they tend to try to estimate it ahead of time given the LESTO data, but they actually use the current magnetic activity at the ground level from these 12 or 13 observatories to make that auroral oval. It's not actually an observation of how much aurora there's in the
Terrestrial.
Right.
Yeah, it's a terrestrial measurement
Well, there's
of the
another piece
magnetic
of that
field.
too. They
Yeah.
will occasionally launch what they call sounding rockets.
Yeah.
That go up a couple hundred kilometers. Also to sample the magnetic field coming into the Earth's atmosphere.
Okay, thank you.
Anything else? Yes, sir.
What about vacuum tubes? Would they be more durable against these storms? Like radio and communications?
Don's nodding yes, and we'll go with him on this. Well, I've never actually looked at vacuum tubes too much, so.
Because I heard, like the Russian airplanes with their avionics, they still use vacuum tubes.
Well, not their more modern. They use
Even
them up
those
as
modern planes still use vacuum tubes.
Well, I think the new, like the SU-26, that one was using microchip, because there's been a big controversy of trying to prevent Russia from using microchips, and that one, it's more of a modern one. But the old, like the MiG-25, so that one used magnetic vacuum tubes and such. So, yeah, the rumor was that they discovered accidentally they hold it better to EMP than anything.
To know where I'm going, I just look out the window.
Wasn't your EMPs shielding that you have to use?
Yeah.
Heavy shielding?
Essentially, they wrap the wires with
Ground
ground and
to keep it from.
fairly cage ground.
Okay, I was reminded that today would have been Carl Sagan's birthday, so.
I wonder who did that.
Something.